Mm, Wait. Okay. I have no video. I logged out. I log out again and sign in. Mm, How come I have no video? Okay. I still don't have a video, so I'll turn off my computer, then restart again. Okay. Okay, I wonder why it does that. Okay, so sorry about last Thursday. I had an emergency meeting. Um, Today we'll just cover and finish the discussion on simultaneous equations model. Oh, when is your exam this week? Thursday?
Friday po.
Friday. Okay. And then you have a Tuesday exam.
Yes po, kay Dr. Bautista.
Yeah. Because I still owe you an hour and a half lecture. So I'll schedule that probably after the reading break. Okay. So let's move on. Um, okay. So last time we went over the estimation methods. We had the system IV for the case where L is equal to K, and for the more general formulation where L is greater than equal to K, we have the GMM methods, the generalized method of moment methods. And examples of these are the system two-stage least squares, which reduces to two-stage least squares equation by equation. If you don't have cross equation constraints, the optimal GMM estimator, where we have the weighting matrix, and the general method of moments, three-stage least squares. Then we contrasted this general method of moments estimator with the traditional three-stage least squares estimator. Then we have the generalized IV estimator. Okay. The generalized IV estimator is not a GMM estimator. Okay. Okay, so for the system IV estimator, we started with the um, model in the OLS GLS form. Y sub I is equal to X sub I beta plus U sub I. Okay. Later on, you will have an example on how you specify this X sub I with the um, endogenous variables, with the endogenous and exogenous variables. Okay. Then we have the uh, two assumptions, the moment conditions and the rank condition. Okay, so if you look at the system IV estimator, the formula is very similar to what we have for the single equation IV estimator, okay, which is C transpose X inverse C transpose Y, okay. Okay. The limitation though of the system IV is that L should be equal to K, okay. Okay, so in Stata, you would be using the IVReg command here. Okay. Then we have the generalized method of moments estimator. And the generalized method of moments estimator can be seen as the solution to this optimization problem. Okay. So if you look at this expression, you have C sub I, Y sub I minus X sub I B. So that is C sub I transpose um, U sub I hat. Okay. Okay. And note that it is of this form where you have B as the estimator for beta. Okay, so you have U sub I hat. Okay. So this is like a sum of squared residuals, but you have this weighting matrix W hat. Okay. So here we have W hat as exogenously given. Okay. And the specific GMM estimator would depend on how you specify this W hat. Okay. So the solution to this minimization problem gives you the GMM estimator, which is of this form. Okay. Okay. So note that this is again similar to the OLS formulation. Our OLS formulation is X transpose X inverse X transpose Y, except that now we have this middle term CW hat C transpose. Okay. Okay, so if W hat is the identity matrix and Z is X, then you would be back to the OLS formulation. Then we have this third assumption, so that we would get consistency of the GMM estimator. And also the asymptotic normality, which gives us the expression for the asymptotic variance of beta hat. Okay. So examples of the GMM estimator would be one, the system two-stage least square estimator, where W hat is specified in this form. Okay? And if you substitute W hat in this equation, then you would get the system two-stage least squares estimator. Okay. In the sure case, the system two-stage least square estimator is the two-stage least square estimator equation by equation. Okay. Then we have the optimal weighting matrix, which gives us the optimal GMM estimator. The optimal GMM estimator is also called the minimum chi-square estimator. So here it is optimal in the sense that we get the estimator with the smallest variance. Okay. So we have the fourth assumption. Okay. So this is the form of the optimal GMM estimator, okay, or the minimum chi-square estimator, and this would be its asymptotic variance. Okay. Okay, so the critical thing here is estimating this lambda hat. So note that this is a function of estimated residuals, which you usually get using the system two-stage least squares estimator. Okay. Okay, then we get the asymptotic variance of beta hat. Okay, so this would be the estimator. Okay, so that is the optimal GMM estimator, or that is also called the minimum chi-square estimator. So the first one was the system two-stage least squares estimator. Then we have the optimal GMM estimator, or the minimum chi-square estimator. And then our third example is the GMM three-stage least squares estimator, where we have a restricted version of the optimal weighing matrix. So for here, we need a fifth assumption about the variance covariance matrix of C sub I transpose U sub I. Okay. Okay. So I've been thinking, in practice, how would you test if system homoscedasticity is satisfied? Usually, um, well, this is a this is a bit different from homoscedasticity when you have a single equation. Okay. So usually in practice, like you would estimate an optimal GMM estimator, or the minimum chi-square estimator, and see how the estimates differ from that using three-stage least squares estimator. If the estimates do not vary too much, then you are not far off from the system homoscedasticity assumption. Okay, so we have here the GMM three-stage least squares estimator. Okay, so it is a bit different from the traditional three-stage least squares estimator, which is derived in this way. You have a matrix of first stage coefficients. Okay. Um, so note that these are like reduced form. These are um, sort of reduced form equations. Okay. So the instruments, instead of just x by hat, would be omega to the minus 1/2. Okay, and this would be the three-stage t squares estimator. So this is so the traditional three-stage t squares estimator. This one is a bit different from the GMM three-stage t squares estimator. Okay. Then we have the generalized instrumental variables estimator, where again, we transform the moment conditions in a way analogous to general least squares. So we have this. So note that it is similar to what we had for traditional three-stage least squares estimator. And we have this estimator. Okay. Now let us compare um, GMM, Generalized Method of Moments Estimation, Estimator, the generalized IV estimator, and the traditional three-stage least squares estimator. In the setting that the traditional three-stage least squares estimator was proposed, okay, so note that all this GMM estimation is more recent compared to the traditional three-stage least squares estimator. Also note that we have not been using maximum likelihood so much. And the recent developments seem to be more in the direction of using the method of moments estimation, uh, which is um, which seems to be simpler than maximum likelihood estimation. Okay. In the setting that the traditional three-stage least squares estimator was proposed, this was in the context of the Schur system with the same instruments in every equation. All the estimates, GMM, GIV, and traditional three-stage least squares are identical. Okay. So if each equation have the same instruments, then all the estimates would be identical, whether GMM, GIV, or traditional three-stage least squares. Okay. The equivalence of all estimates holds if we just impose the common instrument assumption in the general system. This was our model. Let Wi denote a vector assumed to be exogenous in every equation in the sense that, okay, so W sub I would be exogenous in every equation. So that can be the instruments, okay? So the expected value of Wi transpose U sub ij is equal to 0 for each equation, G going from 1 to down to G. Okay? And we choose the matrix of instruments C sub I is equal to I sub G, Kronecker product, W sub I. Okay. The GMM three-stage least squares estimator and the GIV estimator using the same omega or the assumption for the distribution of the use, the variance covariance matrix of the use are identical. Okay. Okay. Furthermore, the GIV estimator and the traditional three-stage least squares are also identical. Okay. The first stage regressions involve the same set of explanatory variables in each equation. And so it does not matter whether the matrix of first stage regression equation is obtained by feasible GLS used by GIV or system OLS used by um, the traditional three-stage least squares estimator. Okay. So if you have the same set of instruments in every equation, then you have the GMM three-stage least squares estimator. This estimator would be identical to this estimator. Okay. And also this estimator would be identical to the traditional three-stage least squares estimator. So it would not matter what estimation method you use among GMM, GIV, and traditional three-stage least squares estimator. In many modern applications, though, of system IV methods to both simultaneous equations and panel data, instruments that are exogenous in one equation are not exogenous in all other equations. In such cases, it is important to use GMM, three-stage least squares estimator, once C sub I has been properly chosen. Okay. Then if you do not have, if the set of instruments vary across equations, then you're better off using the GMM three-stage least squares estimator. Now let's go to testing. Okay. Um, we just consider the linear hypothesis of this form, R beta is equal to R. So we have Q linear restrictions. So R is Q by K because we have K parameters in beta. Okay. So beta here is K by 1. R is Q by 1. And furthermore, we assume that Q is less than or equal to K. So the number of restrictions cannot be more than the parameters that we are estimating. Okay. Then you can use the Wald statistic, which is R beta hat minus R transpose, R V hat, R transpose inverse, R beta hat minus R, where you have V hat is the appropriate estimate of um, of the asymptotic variance of beta hat. Under the null hypothesis, W is asymptotically distributed as chi-square with Q degrees of freedom. Okay, so note that this is the Wald statistic. You would often, in higher level econometrics, once we get out of the OLS, Gauss-Markov framework, we usually use the large sample test, the likelihood ratio test, the Wald test, and the Lagrange multiplier test. So the Wald test has the property that it uses only information on the unrestricted estimates. So beta hat here is unrestricted. Okay. And note that it is in the test where the asymptotic variance of the estimator, the asymptotic variance of the estimator comes in. Okay. If you are using the minimum chi-square estimator of the or the optimal GMM estimator, we can use a test based on the change in objective function when the restrictions are imposed. Okay. So note that earlier I mentioned the optimization problem. We're minimizing some function. So that is the objective function. So we would like to see the change in the value of the objective function when the restrictions are imposed. So here you would need the restricted estimator, beta curve, using the same weighting matrix W hat. Then under the null hypothesis, it can be shown that you're looking at the difference in the values of the objective functions. Um, so note that we have, let's go to page 12. Okay, so note that you have this. So if you substitute the appropriate estimator, and you get the estimate, you get the value of this objective function. Okay. As I said, this would be um, the estimated residuals. Okay, so you get the difference between the estimated between the values of the objective functions. And this would also be asymptotically distributed chi-square with q degrees of freedom. Okay. Okay. Note that chi-square statistic, if you have q of this, the degrees of freedom, you're really summing q standard normal random variables. Okay. So note that really this is some form of sum of squares. Okay. Now suppose you have the GMM three-stage least squares estimator, then you just replace W hat here with the appropriate W hat, and the statistic would reduce to this. Okay. Okay. Because for the GMM three-stage least squares estimator, we have um, okay, so you can get W hat from here. Okay. Okay. Um, this part is just equal to this. Okay. Okay. The sum of C sub I transpose omega hat C sub I, where omega hat is the estimate of the variance covariance matrix of the U sub i's, the disturbances. Okay, so note that you get it here. Okay, so you get this expression here. Okay, somehow the n, this n minus 1 would cancel with the n minus 1 here. Now you can also look at the test for over identifying restrictions. You have over identifying restrictions if the system is over identified, L is greater than K. That is, the number of instruments is greater than the number of parameters you are estimating. And again, this is also based on the value of the objective function. Okay. Okay. This is based on the value of the objective function, not the difference anymore. Okay. Note that under this null hypothesis, so this is just the first assumption on the moment condition. Okay. And this left-hand side here would be asymptotically distributed chi-square, but now with L minus K degrees of freedom. Okay. Well, you just substitute the optimal, what you just substitute what W hat you use. Okay. Generally, if we start with moment conditions of this form, okay, which is just the first assumption, GMM estimation based on this set of moment conditions will be more robust than estimators based on transformed set of moment conditions, such as the GIV. Okay. Note that when we derive the GIV, they are based on a transformed set of moment conditions. We have that omega to the minus 1/2. Okay. If we decide to use GMM, we can use the unrestricted weighting matrix. Okay. Under system homoscedasticity, this assumption, the GMM three-stage least square estimator is an asymptotically efficient GMM estimator. Okay. When the same instruments are used in every equation, GMM three-stage least squares, GIV, and traditional three-stage least squares are identical. We mentioned that already earlier. Okay, that is when the same instruments are used in every equation. GMM three-stage least squares, GIV, and traditional three-stage least squares are identical. Okay, so you use GMM three-stage least squares only if the system homoscedasticity assumption is satisfied. Okay. Note that we did not use this assumption when we had the minimum chi-squared estimator. Okay. So you can look at GMM three-stage least squares as a restricted version of the optimal GMM estimator. When GMM and GIV are both consistent but not square and asymptotically equivalent, they cannot generally be ranked in terms of asymptotic efficiency. Okay. Okay, because asymptotic efficiency would also depend on the variance covariance, the asymptotic variance covariance matrices of the estimators. Okay. Adding more instruments that are exogenous, of course, instruments should be exogenous, can never hurt asymptotic efficiency, provided an optimal weighting matrix is used. Okay. So if you use optimal GMM or GMM three-stage least squares, if you add more instruments, it does not hurt. However, recent research has shown that adding lots of poor IVs can seriously deteriorate the asymptotic approximations of GMM estimators. Okay. Uh, Note that for IVs, we want them to be uncorrelated with the disturbance term of the equation, but highly correlated with the variable that they are being used for as instruments. Okay. What about system two-stage least squares and GMM three-stage least squares? Under system homoscedasticity, three-stage least squares is generally more efficient. Okay. But there are situations where they coincide. Okay. So these are two cases where they coincide. One is if the system is just identified, that is L is equal to K, all estimators reduce to the SIV estimator. In the case of the Schur system, the system is just identified if and only if each equation is just identified and the rank condition holds for each equation. Okay, then you can just use system two-stage least squares, and which reduces to two-stage least squares equation by equation. You would, if you do GMM three-stage least squares, you would get the same result. Okay. Okay. When estimating the Schur system, the three-stage least square estimator is equivalent to two-stage least squares equation by equation, regardless of the degree of identification. That is, even if L is greater than K, when omega hat is a diagonal matrix. That is omega hat, which would have diagonal elements, these diagonal elements, and zero off diagonal. Okay. In this case, two-stage least squares and three-stage least squares are asymptotically equivalent. Okay, so if L is greater than K, but the disturbances across equations are not correlated, then um, you have three-stage least squares estimator is equivalent to two-stage least squares equation by equation. So those are just special cases. And repeatedly that comes out in our results. Life becomes much simpler if L is equal to K. And if the off-diagonal elements of the variance-covariance matrix of omega, the disturbances is zero. Okay. In cases where two-stage least squares on each equation is not algebraically or asymptotically equivalent to three-stage least squares, it is not necessarily true that we should prefer the three-stage least squares estimator or the minimum chi-square estimator. Okay, or in other words, it does not mean that we would prefer a system method. Okay, because even for a system method, we assume that or generally require that the expected value of C transpose G, U sub G is equal to zero for all G, not just for the equation of interest. Okay. So if we have a system of 5 equations, we're really just interested, let's say, in the third equation. For a system procedure, we require that for every equation, the instruments are uncorrelated with the disturbances. Okay. We require that for a system procedure, not only in the example, the third equation. Okay. As with system OLS and feasible GLS, there's a trade-off between robustness and efficiency. Okay. Robustness means that we use in a single equation approach is not so sensitive to misspecification in the other equations. Okay, so here we see for a system procedure, we have this requirement. Okay, and efficiency, if the equations are correctly specified, then the system procedure can give you more efficient estimates. Okay. You might want to go through Cameron and Trivedi, the Cameron Trivedi book, Microeconomics Methods and Applications, Chapter 6 on the generalized method of moments and system estimation. Okay, it's a shorter chapter compared to Wooldridge chapter. Now let's see how cross-equation restrictions and restrictions on the variance-covariance matrix can help identification. Though there are really rarely cases of cross-equation restrictions and variance-covariance matrix restrictions in simultaneous equation models. Okay. Okay, so most applications of pure SEMs have restrictions within each equation, but not across equations. Okay, because in SEMs, usually you have autonomous equations. Excuse me. Excuse me. Nico, I'll call you later. Nico, I'll call you later. Okay. Okay, so for example, in the labor supply wage offer model, it would be hard to justify assuming that parameters in the supply and offer functions are related. Okay. Nevertheless, let's consider a simple example to show how cross-equation restrictions can help with identification. Okay. It's just also to illustrate how you can tweak your estimation methods. Okay. Suppose you have a two equation system. Okay, so we have y sub 1 and y sub 2. Okay, so y sub 1 is a function of y sub 2. Y sub 2 is a function of y sub 1. So y sub 1 and y sub 2 are endogenous. Okay, then we have, for equation 1, the exogenous variables are c sub 1, c sub 2, c sub 3. For equation 2, the second equation, we have c sub 1 and c sub 2. Okay, so we have the usual assumption that the z's are exogenous, therefore the z's are uncorrelated with the corresponding disturbances. Okay, so C sub 1, C sub 2, C sub 3 are uncorrelated with U sub 1. C sub 1, C sub 2 are uncorrelated with U sub 2. Okay, without further restrictions, the first equation is unidentified. And the second equation is just identified if delta sub 1, 3 is not equal to 0. Okay. Right? So the first equation is not identified. The second equation is identified if delta sub 1, 3 is not equal to 0. Here you would be using C sub 3 as the instrument for Y sub 1, right? Suppose now we have the restriction delta sub 1, 2 is equal to delta sub 2, 2. Okay. So we restrict that these are identical. Okay. Because data sub 2, 2 is identified without restrictions, okay? Because data sub 2, 2 is identified without restrictions, we can treat data sub 2, 2 is equal to data sub 1, 2, as known for determining the identification of the second equation. So we can rewrite the first equation as follows, okay? So we can move delta sub 1 to C sub 2 to the left-hand side because delta sub 1, 2 is known to be equal to delta sub 2, 2. So we have y sub 1 minus delta 1 to z2 is equal to, then we're just left with the 4 terms here. Okay. Okay, so we can treat this as known. Okay. Note that you have data on y sub 1, y sub 2, C sub 1, C sub 2, C sub 3, but this delta 1, 2, we assume to be known because we know delta sub 2, 2 from equation 2, okay? So if you look at this equation, this is now identified. What can we use for the instrument? Y sub 2 is still endogenous. What can we use as the instrument for Y sub 2? Then for Y sub 2, for Y sub 2, we can use as instrument C sub 2, okay? Provided that delta sub 2, 2 is not equal to 0, okay? So we have a two-step procedure. First, estimate data sub 2, 2 by instrumental variable on the second equation. So first estimate the second equation. And you can do that by instrumental variable where you use C sub 3 as the instrument for Y sub 1. Then you get an estimate for theta sub 2, 2. Okay. Okay. But that estimate for theta sub 2, 2 would be also the estimate for theta sub delta sub 1, 2. So you can form on the left-hand side for the first equation this dependent variable. Okay. And now you can estimate this again. So this is known. We have data on y2, c sub 1, c sub 3, and the IVs. For y sub 2, your instrumental variable would be c sub 2. Okay. So you can estimate the to the structural parameters. Okay. However, an alternative way is using a system approach. Once we know both equations are identified, it's better to use a system method. Define the vector of unrestricted parameters as this. Okay. Gamma 1, 2, delta sub 1, 1, delta sub 1, 2, delta sub 1, 3, gamma sub 2, 1, delta sub 2, 1. Okay. Note that we don't have any more delta sub 2, 2 because um, we have that to be equal to delta sub 1, 2. Okay. For a random draw I, we can then rewrite the equation in this form. Okay. So you can check it out given this beta. Okay. Note that this beta is a 6 by 1 column vector. Okay. So here you have x here as uh, x here would be the um, would be the uh, 2 by 6 matrix coefficient x sub I. Okay. 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 So on the left hand side we have y sub I, which is really a 2 by 1 vector. Beta is a 6 by 1 vector of parameters that you would like to estimate. Okay. So we have 2, 4, 6. Okay, so we have 2, 4, 6, 7, but we have the restriction here. So we're left with 6 parameters to estimate. Okay, then we have the disturbance term. Okay, so you can carry out the matrix multiplication and see if you get this system of equations with the restrictions. With the restriction, delta 1, 2 is equal to delta 2, 2 imposed. Okay. And then you have the matrix of instruments, which is the 2 by 2 matrix Kronecker product C sub I, and you would get this. Okay. The system is just identified, so the system IV is the only estimator. That is the first estimator we have. Okay, so we reduce so this is a case where L is equal to K. So you can use the system IV estimator. Okay. Okay, so that's just an illustration, a simple illustration on how restrictions, cross equation restrictions can help with identification. Though in most SEMs, um, you rarely have cross equation restrictions. Okay. Next, let's look at covariance restrictions as another source of identifying information. Okay. Um, we have covariance restrictions, and the restrictions are usually of the form that some errors or disturbances have zero covariances. Okay. We rarely have restrictions on the variants themselves. Okay. So it's more on how, if you have this two equation model, how u sub 1 and u sub 2 are correlated. Okay. Okay. For example, consider this system. Okay. Okay. So in y sub 1, we do not have c sub 2. In the second equation, we have all three exogenous variables, c sub 1, c sub 2, c sub 3. Okay. Without further restrictions, the second equation is not identified, and the first equation is identified if delta sub 2 2 is not equal to 0. C sub 2 can be used as an instrument for y sub 2. Okay. So assume that delta sub 2 2 is not equal to 0. Okay. Because if delta sub 2 2 is not equal to 0, then C sub 2 is not correlated with y sub 2. So that would not make a good instrument for y sub 2. Okay. Suppose, however, that the covariance of u sub 1 and u sub 2 is equal to 0. Okay. Because of the zero mean assumptions, zero conditional mean assumptions, this covariance we just with the expected value of u sub 1, u sub 2. Okay. So if the covariance is 0, you have two disturbances here, then the off diagonals would be 0 and the sigma matrix would be diagonal. Okay. And this assumption would serve to identify the second equation, which is not identified. Okay. Let us see how that works. Okay. Because the first equation is identified, we can treat all the parameters of the first equation as known for identification of the second equation. Okay. So we can rewrite u sub 1 as y sub 1 minus these other three terms. Okay. So u sub 1 is equal to y sub 1 minus gamma sub 1 to y sub 2 minus delta sub 1 1 c sub 1 minus delta sub 1 3 c sub 3. Okay. And u sub 1 becomes an observable variable. Normally, being able to effectively observe u sub I would not help with equation 2. Okay. But if we assume u sub 1 is uncorrelated with u sub 2, u sub 1 becomes a potential instrument for y sub 1. Okay. Note that for the second equation, y sub 1 is the endogenous variable on the right-hand side, and we can use u sub 1 as an instrument for y sub 1. Okay. U sub 1 would be correlated with y sub 1. Okay. Note that u sub 1 affects y sub 1. Okay. So if we assume u sub 1 is uncorrelated with u sub 2, u sub 1 becomes a potential instrument for y sub 1. Okay. Okay. U sub 1 is correlated with u sub 1. U sub 1 can be used as an instrument for y sub 2, but u sub 1 must not be correlated with u sub 2. Okay. Okay. Do you get it? What are the two conditions for an instrument? Um, you have relevance. So U sub 1 affects Y sub 1. So U sub 1 and Y sub 1 are correlated. Okay. So U sub 1, if you use an instrument for Y sub 1, the second condition is U sub 1 must be exogenous, uncorrelated with U sub 2. Okay. So therein comes in the assumption of the zero covariance between U sub 1 and U sub 2. Okay. Okay, so we have a two-step procedure. Therefore, for Y sub 2, you can use Y sub U sub 1 as the instrument. Okay, so you have a two-step procedure. First, you estimate this U sub 1. Okay, and you can estimate this U sub 1 by estimating this equation. Okay, and this equation, the first equation is identified. Okay, the first equation is identified. Okay, so estimate the first equation using C sub 2 as the instrument for Y sub 2. Okay, so that is the first step. Estimate the first equation by IV with instruments C sub 1, C sub 2, C sub 3, and then get the residuals. Okay, then estimate the second equation by IV with instruments U sub 1 hat, C sub 1, C sub 2, C sub 3. Okay. Um, a better approach, but this would lead to nonlinear GMF, is a system approach. Okay, that is we use all the moment conditions at once. Okay, let beta 1 and beta sub 2 be the structural parameters in the first and second equations with the restrictions already imposed. Then the moment restrictions we have are, okay, so we have the expected value of C transpose U sub 1 is equal to 0. The expected value of C transpose U sub 2 is equal to 0. Okay. Here I have U sub 1 is a function of beta 1. U sub 2 is a function of beta 2. So that is, okay. So the notation is used to emphasize the moment conditions depend on the parameters. Okay. So the first two sets of our restrictions are the standard ones, the orthogonality, the moment conditions or orthogonality conditions. And the third condition here is the zero covariance assumption. It is simply this, okay, where where I have U sub 1 and U sub 2 as functions of the betas. Okay, so we have three equations here. Okay, because we have three because we have three instruments and we have three equations here because we have three instruments. And then we have one restriction here or one equation. Okay. So beta 1 has three unknown elements and beta 2 has four. Okay. So that is here. You have three structural parameters. Here you have four structural parameters you would like to estimate. So there are 7 unknown parameters. There are those 7 total restrictions. So the method of moments estimation would now be nonlinear in the parameters because of this third restriction. Okay, so we would not go into that anymore because that would involve nonlinear GMM. Now, an example where we have these covariances equal to 0 is the recursive system. And you would see this also in some models. Okay. A recursive system has a sequential, I should have included. Okay, I'll just correct it later. This is a recursive system which illustrates a sequential decision-making structure. Okay, note that in this system of equations, you have all the exogenous variables show up in each equation. So you have z appearing in each of the equation. Okay, y1 does not depend, y1 depends only on z, y sub 2 depends on y1 and z, y sub 3 depends on y1, y2, and z, and so on. So y sub g depends on y1, y sub 2, down to y sub g minus 1 and z. Okay, and you have disturbances for each of the equation. Okay, note that the first equation is always identified because on the right hand side you only have exogenous variables z. Okay, but that would be the only identified equation without more assumptions. That would be the only identified equation in the system. We need more assumptions for each of the equations to be identified. Okay. A fully recursive system as the equation, expected value of u sub g, u sub h is equal to 0 for all g not equal to h. So that is the covariance between any two disturbances where the disturbances do not belong to the same equation. So u sub 1 and u sub 2 are uncorrelated. U sub 3, U sub G are uncorrelated. U sub 2, U sub G are uncorrelated, and so on. Okay, so that this would add identifying conditions. Okay, okay, so using the um, using our intuitive or rough way of getting estimates uh, outside the system approach, you can do sequential estimation. Okay, start with OLS for the first equation. You can, because that is identified, right? And using the residuals u sub 1 hat, then use u sub 1 hat as the instrument for y sub 1. Okay, in the second equation. Okay, then for the third equation, you use u sub 1 hat for the instrument for y sub 1, u sub 2 hat for the instrument for y sub 2. Okay. Therefore, you can estimate the equations sequentially. Okay. Again, you can use joint GMM, but then the moment conditions lead you to nonlinear GMM estimation. Okay, do you have questions?
None, ma'am.
Okay. So Charles will give you a problem set on simultaneous equations.
Kakabig, next week yung deadline nung sa SUR, pina-extend nila
Okay. Yeah. Yeah.
After na pero gagawa na rin for SEM.
Yeah. Mm-hmm. So for SEM, let's have examples of GMM, GIV, and three-stage least squares.
Okay, ma'am. Theoretical and applied.
Yeah. Mm-hmm. Yeah. Maybe they can work on that during the reading break. Ano exam nyo? Macro this Friday and
Yes.
monetary Tuesday next week. Okay.
Yeah.
So I'll stop here, and that ends our discussion of simultaneous equation models. Tomorrow we'll start with panel data methods. I'll see if I can get a more simplified approach, simpler than what Woolridge has. Okay, but then because actually in Woolridge he takes the panel data under systems of equations also. Okay, so it's like actually in panel data you just have a single equation, but then Woolridge analyzes it using the system equation, where instead of having different equations, you have different equations. You have equations per time period. Okay. So if you have 10 time periods, then you have 10 equations. Okay. But maybe we do not need that complication to get to study panel data methods. Okay.
Ma'am.
Yeah.
So we'll have another makeup class. Yeah.
What's that, JF?
We'll have another makeup class.
You
And
have not. Do we have
Makeup
not?
class daw, ma'am.
Ano yun?
Makeup class daw.
Yeah, yeah. But then you have we have classes Tuesday, Thursday, but you have your exam on Friday and you have exam on Tuesday. So when would you like the makeup exam? Shortly after Wednesday, or Wednesday after your exam next week? Kailan ba start ng reading break? Technically.
29.
60 po, ma'am. 29.
29. So we can have a makeup class Wednesday. You have class on Wednesday.
Pwede naman po ako, ma'am, ng hapon. 3 to 3 o'clock.
Oh, sige. Wednesday. So,
Ay, pero may 209 class po.
Yeah.
oh,
Yeah.
Morning. Ay, di pala may macro class pala.
Ano no?
8 a.m. Mga 8:30, ganun. Kung
Ano time class nyo?
maaga.
Anong time class nyo? 10?
First class po is 10. Yeah.
And then in the afternoon?
May ano po kami kay Dr. Escresa. History of Econ. 4 to 5:30 po.
4 to 5:30. So you want 1 to 2:30? Meron ka lang. Or we can have it after the reading break if you wish.
I think meron na lang.
Ano?
After
After the reading break.
po siguro. Yeah.
Okay. So after the reading break. Okay. So let's set it Friday. Ano, may class pa kayong Friday? Or the following Monday na lang ulit. Diba? Friday, May 10, afternoon.
Siguro po ma'am morning na lang. Like 10 o'clock. Yung Monday, May 10 niya.
We usually have faculty meetings kasi Monday mornings.
So kailan po yung midterms?
Ano?
Yung midterms po.
It would be after panel data.
Pero wala pang pong date exactly.
We can have it May 10 para may excuse ako hindi mag-attend ng faculty meeting. Morning?
Yeah.
May 10 morning, 10 a.m.
10 a.m. Yeah. Game po ako dyan.
Okay. O sige. Kasi Friday would not be too good for you. May classes pa kayong Friday? Okay. So May 10 na lang. 10 a.m. That's okay?
Yes po, for me po. Okay po yan.
Okay. Sige. Okay. So I'll see you tomorrow. We'll be starting with panel data. Okay. Well, yeah. So I think for me, the most difficult topic really in the course is these systems of equations, simultaneous equations, because you are looking at multi-equation models. Okay. So hopefully it would be easier. Well, yeah, might be easier. Kaya lang, yeah. Mhm. Kasi later on, it's just single equation. We're back to single equation. Okay. Okay, so I'll see you tomorrow 10 a.m. Okay.
Thank you po, ma'am.
Yes, ma'am.
Thank you, ma'am. Charles,
Yes, ma'am.
ano, i-send ko sa iyo yung yung sa point distribution sa
Yes,
oo. Pero ano,
wala akong email nung bagong staff.
anong bagong staff?
Yung pumalit kay Tita Marcy.
Si Azil. O sige, ibigay ko sa iyo yung
I-edit ko pa kasi may mga students hindi naglagay ng name sa paper.
Oh.
Sa file name lang. Eh baka malito dito. I-edit ko pa.
Hindi mo nilagay dun sa instructions. I think dun sa 231 nilagay natin yun sa instructions.
Nilagay, alam mo naman minsan.
Oo. Saka yung page numbers, di ba? Kasi
Ayun, no, yun, okay, yung page numbers okay naman.
oo.
Na-check ko yun lahat.
Oo. Kasi nakakainis dati merong ayun sa comps, yung iba yata hindi naglagay ng page numbers, hindi, kasi minsan di mo alam kung may na-miss ka, di ba?
At yung page number, chinek ko talaga. Yung name nakalimutan ko i-check.
Oo. Yung, yung kasi yung kay Hazel. Actually, I haven't met her. Sa email ko lang na Pero okay naman yata siya. Oo. Yung sa 106, 10 points per problem, pero isusulat ko yung
Sige, ma'am.
yung point distribution. Dapat mas strict ka dito ng checking compared to the problem sets. O sige. May utang pa ako sa'yo. Except the point is,
Wala naman. Ako, wala naman.
ay nako. Mm-mm.
Gumawa na rin ako ng ng answer sheet.
Madali lang.
Sinagutan ko lang. Madali lang naman.
Yung number 1 tsaka number 6, ang problem sa number 6,
Ayaw, maraming blanks sa number 6.
pero it's really a simple problem. Kasi they do not know how to set up the problem. Di ba? Yun ang, pero it's simple, di ba? Yun ang difficulty doon. Sige, email ko sa iyo yung point distribution. Mga ilang pages per student ang sagot nila? Mga 3 or 4?
Ganun. 5.
5. Sige. Pagkatapos minsan hindi clear pag dark yung paper, pag yellow pad.
Ano ba?
Tsaka,
Parang ilan lang, parang 1-2 lang naman kung kami ng yellow pad.
and then yung, yung, hindi clear. Tsaka yung iba, masyadong maliit yung sulat, yun nagiging problema. Maski expand mo sa computer, parang hindi mo pa rin ma-decipher. Merong 2 estudyante na may isa, ewan ko kung ano yung grandmother niya namatay, kaya she went to the wake. Yung isa na COVID, yung isa na dengue. Anyway, okay lang yun kung...
So, 2 lang yung meeting natin eh.
Oo.
Yung isa nagsabi na sa akin bago pa. Yung isa, parang hindi siya talagang kaparamdam eh.
Oo.
Yung isa.
Oo. Hindi bale, tignan na lang natin after. Sige. Okay. So, yun lang.
Yung midterms, after reading break na, 233.
Sa 233? Oo, para after panel data. Kasi 2 lang exam set, di ba? Matagal pa yata itong online natin. At least hanggang next sem, di ba? Kasi I don't see having in-person classes pag pag wala pa yung herd immunity. Di ba? Tsaka kasi with the current vaccine, hindi ba yung Sinovac, its efficacy is quite low, kaya you still have to take precautions.
Pero yun si Miharu, si Miharu, parang convinced naman siya sa Sinovac.
Sino si Miharu? Yung...
Econ PhD, pero doctor din.
Oo. Doktor ba siya? Medical doctor?
MD. Tsaka Derma board.
Derma?
Pero hindi niya tinuloy eh. Nag-PhD siya sa
Ano ginagawa niya ngayon?
Nag-dissertation.
Ano yung dissertation niya?
Health eh. Research Colon Advisor. Hindi ko alam yung technical. Hindi ko alam yung details.
Oo. Well, talaga, it's mostly what is available, yung science.
Dahil may nabasa ako, parang yung efficacy, depende rin sa timing ng clinical trials. So kung mataas yung kung malaki yung mobility noon, most likely mababa yung efficacy pag during times na walang lockdown ng clinical trials. Kasi factor yun sa Pfizer and Moderna eh, para naka-lockdown ng clinical trials. Kaya mataas yung efficacy.
Pero grabe sa stage, yung mga tao doon, they dine in, parang, yung iba hindi masyado nagmamask. Even naman yung royal family, when they do their parang, yung sa England, minsan hindi sila nakamask. Diba?
Pero yung parang sila pinapromote na yung vaccine eh.
Oo. Yeah. Oo.
Yung royal family.
Mm. Ayan, compare sa atin, mataas na yung vaccination rate nila.
Oo.
Ang
Wala
Canada,
eh. Ayun, parang yung problema rin sila sa Canada.
oo. Yung Canada,
Sa Canada.
yung friend ko na-vaccinate siya earlier this week. Yung first dose ng Moderna. Well, matagal din siyang nag-apply for the vaccine. Pero the second dose would be 4 months.
4 months? Ang
Oo.
tagal.
Oo. Kasi,
Parang mga 40 days lang yung ano ah.
Ah.
Bakit matagal?
oo. Charles, yung Novavax, may narinig ako, hindi ba yun yung sa,
India.
oo, tsaka yun yung sa, actually sa US firm, it's just that the manufacturing is done. Yeah. Pati yung Astra, may manufacturing din sila sa, sa India. September pa yata yung Novavax, sabi ni Joey Concepcion.
Wala pang EUA yun eh. Wala pang wala pang FDA.
Siguro 3 weeks to a month at most. Pero ang tagal pa yung Novavax.
Nakasign up din ako sa UP eh.
Oo. Ako rin
Saka sa LGU.
Saan? Sa LG.
Sa LGU.
Ang Makati magaling. Kasi maraming vaccination centers sa Makati.
Parang kada barangay. Pero dito sa barangay namin parang meron nata mismo.
Kaya lang bata ka pa unless may comorbidity ka.
Hindi naman nung nag-apply. Kasi kailangan ng med-cert dun eh.
Oo. Yeah. Grabe. Kaya, iyon, kaya i-set ko sa yung email, ni Asil.
Bakit? Diba?
Sige. So bukas, no? So, i-change mo yung invitation ulit sa para bukas, sa 233.
Hindi, meron na yun.
Meron na yung...
Meron na yun.
sige. Okay.
Okay, ma'am.
Yeah, see you.
Okay, ma'am.